And finally, our trailblazer. Fran Allen is Senior Manager of the Parallel Software Department in IBM's T.J. Watson Research Laboratory. And she has been a trailblazer in the whole area of compiler design. She was a designer and manager on the Stretch Harvest compiler project, the Experimental Compiling System project, and a number of other systems. She's also a fellowess 3 times over. She's an IBM Fellow, an IEEE Fellow, and an ACM Fellow. And with that, I will welcome our jolly good fellow, Fran Allen.
Thank you very much. Well, ladies and gentlemen, I am very delighted to be here this morning, and delighted in particular about the fact that I'm speaking at a Hopper conference and speaking at compilers. The very first compiler that was ever built was built by Grace Murray Hopper, and it was completed in 1952. It's a wonderful history. And one of the things I'm wanting to do this morning is to share with you the wonderful history of compilers, which I've been involved with since 1957, and how it affects the relationship between that and computer science, and how our field has developed. And I want to give you some personal insights into how I've been, how it's my own work in this, and how my own career has kind of been interwoven with some of that. It's going to mix some history and some personal observations, and I hope we have some time at the end so we can have a little bit of discussion. The challenge in 1954, and notice this is 2 years after Grace Murray Hopper had finished her first compiler, is given here in terms of a performance challenge. It's given by John Backus, whom I think all of you know, did the first FORTRAN compiler. It was to produce programs almost as efficient as hand-coded ones, and to do so on virtually every job. Okay. Now, how successful was that project? It had some amazing results. First of all, it came out in 1957, having for the 3 years in between been 6 months to completion. And I'm sure we've all been on projects like that. They're always going to be completed in the next 6 months. But this project had a profound effect then on the way we do computing, and was probably the single biggest result that affected software. The main reason being is that it established the feasibility of high-level languages. Just overnight, it changed the way we were expressed the solution of problems to computers. It did that by establishing a standard of object code efficiency. And the focus of the entire project was to raise the level of problem expression, and the people that were involved with that project, I wasn't, knew that in order to do that, they had to be as good as hand code, and they were. And they also, at the same time, established modern compiler tasks and structures. All of our techniques that we use today, not all of them, many of them have their basis in that project, in the work that was going on at that time. Let me just give you an example just talk through this example a little bit in terms of what kind of code they would produce for this very simple, for the sake of the example, a move of an array, a two-dimensional array. The machine that they were compiling for had just 3 index registers. And those of you that have looked deeply at compilers, and probably all of you have taken the freshman course in compilers, you might want to take a guess at how many index registers would be used for this. The fact of the matter is only 1. You could actually use, they fuse the loops, the 2 do loops. They use only one register, use one for B, the same one for A, the same one to decide to go around, whether they were finished with that fuse loop, and came out with one register. So there's very few compilers today that are that good. Of course, it was a simpler point of view, but remember, were no technologies in place at that time. It was an amazing piece of work. In fact, a number of years after this, when I was looking to starting the work on the theory of program optimization, I was looking at this particular example. And my first thought, I was just going through lots and lots of code, and my first thought, this is wrong. Their result is wrong in here. They've made a mistake. And it took and I never got the theory quite right to handle this case. It's still a little bit ad hoc here in this area. Now, the next chart shows what the structure of that compiler is. And you can see in this kind of the beginnings of the compiler structures that we have today. The numbers down on the left-hand side of the phases. The first, essentially the first two phases are parsing in some sense. The identification of the statements and parsing. And then the third phase is because the first part didn't match the second part. And it is, and I think we've seen that over and over again. I've looked inside compilers, and very often the pieces don't match. So we put in glue code, we put in something in order to get them together. And that's what happened in this particular project. After that, there was an analysis phase, and there was a register allocation phase, the final assembly phase, and all of these phases, in one form or another, one sees in modern compilers. And in fact, the low-level intermediate form that was used also exists in modern compilers. And if one goes back into the literature here and into looking at what was inside this, one finds the beginnings of the whole theory of parsing. And the very first paper on that, one sees the author struggling with what is a parser, trying to abstract out of that. And of course, in Bacchus, a couple of years after this project, I think it was 3 years after this project, then actually came up with the Bacchus normal form or Bacchus-Nauer form, which was the formal specification of grammar of how to specify grammar, and out of that came this marvelous pieces of work in parsing. One of the things that I've noticed over the years is that in compilers, which because it's been an active field, both in theory. In developing the science, but also in terms of products, that how the ideas have evolved. And there's an interesting cycle, and the parsing work is a good illustration of it. There's a problem that arises. Somebody's trying to build a product. A problem comes up. There's no solution for it. It doesn't exist in the papers. It doesn't exist in the prior art. And so the builders do something ad hoc. They often have to struggle to define just exactly what the problem is, define what the problem is, frame it. That's sometimes the hardest thing that is done, is isolating the problem, breaking it up into component parts for which there can be solutions. And one saw in parsing, one sees struggling out of this first compiler here in the early compilers, the notion of how to do this. And then one starts to see, in starting the theory starts to build, the science starts to build behind it. And this is often where the computer science people pick up on these problems and then build these beautiful theories that have carried this field and the rest of our work in computer science so far. But then there's often a gap before it gets back into products. Sometimes these theories are not very relevant, or sometimes the people who are working in products don't recognize the value of them. Sometimes they're abstruse. They're not expressed in quite the right way. They're not expressed in a way that is relevant. Or maybe they aren't really very pragmatic. One of the things that I've noticed is that there have been, early on, there were kind of 10-year lapses almost from problem identification back in, you go through theory, and then you go back and you start to see it coming up in products again. I think that is being short-cycled right now, which is terrific. And I think one of the reasons it's being short-cycled is, and the cycles are much shorter, is that people who have training in computer science are actually out there building a lot more compilers than it existed before. So that it's really a matter of a much closer relationship between the theory people and the computer science people and the people who are building the products. It's really a very nice development. And the same thing has happened throughout, but these cycles are rather interesting to follow, and there's a thread of these ideas in compilers and elsewhere, which it would be interesting to do, I think, some work on that. So what has then happened since this work in 1957? Since this was such an astounding result that came out at that time. Well, of course, we have greatly improved algorithms there. And I'm going to give an illustration of what's happened in one particular area. But the algorithms that have been developed are sometimes actually at the breaking edge in terms of speed and correctness. Very, very interesting development. We have new models of computation. One of the big results that has happened, of course, is virtual memories. The idea that we don't have to worry very much about real memories any longer. We've partitioned that particular problem up. The models of computation that arise as a result of the way the programming languages are written. In fact, I think that this is an area we need to focus on quite a lot more. We have layers of models of computation in our systems. The hardware itself provides a model of computation. There's a layer often that the operating system then provides. It's a model on which we build usually our compilers, the compiler output, or actually the runtimes provide, the compilers provide, have a model of computation. And then the languages themselves have a model of computation. And sometimes if languages are very high level, then that model of computation is a great distance from the computer. And one of the jobs of the compiler is to change the model of computation. Now, of course, we go in kind of traditional high-level languages. We go from arrays to indices. We linearize the arrays and so forth. But the distance is even greater when we start to put parallel machines underneath. We have to go from programs that have been written for maybe for single thread machines, and we want to get them on parallel machines. Now, Mary Jane Irwin this morning raised some interesting some challenges about having to write a compiler for the massively parallel machine that she's been working on. These models of computation, these changes in the models of computation at different levels are coming up all the time. And I think we have to concentrate on that itself as an area we should look at. How do we move from one model to the other? We also have, of course, many new languages and language features. I might say that I've been very disappointed, in fact, in what we have done in the last 40 years in terms of languages. I don't think we've come very far. I think we ought to be ashamed of this. We are still working with very primitive languages. I believe that the purpose of program optimization is not so much to make the machines run faster. That's a means to an end. The end is to be able to have much higher levels of expression of the problem and still be able to take advantage of, get the kind of speeds and performance that one wants. No. So I think we have not moved with languages, and there certainly have been some wonderful and interesting languages that have come along, and we may be on the verge of that now. I mean, I think object-oriented is very interesting. If we can put some, but it's interesting as a concept. We're still struggling with expressing it at much too low a level. and the compilers are having trouble with these languages, and we're just not getting very far with this. I think I think the visual languages moving up to a much higher level is very important. We have, of course, the new architectures of all sorts, and connectivity. That's just starting to emerge. It's pervasive, but we're starting in the compiler world, I think, and in the language world to start to deal with it in some more consistent way. We're seeing in the in operating system world having networks of operating systems, network operating systems, which manage the whole network. We need to be able to look at the way we write programs, and think of it as being executed invisibly on a network of computers. But we're quite a long ways from actually being able to do that. And environments are extremely important, and the whole world of computer science has started from after FORTRAN 1. Several years after FORTRAN 1, and the science has very much emerged there, as I've mentioned earlier. Let me turn then to the history of one idea, that program analysis. It is work that goes on inside a compiler in order to be able to understand the relationships. And it's kind of essential to understand how data and control flows within the compiler in order to be able to modify it, to change it, to take it apart, possibly run it, find parallel units and run it on other parts of this, on other computers, distribute the data, distribute the work. And this is an example of a cycle of how ideas can cycle and change. Here's in this first chart, we've just shown a fragment of a program. The nodes indicate statements in the program, and the edges represent control flow. Think of the nodes as being basic blocks or just statements, whatever you want. And then we have various definitions of X, one in node 3, one in node 6, one in node 8, and a use in node 5. And this is exactly this form appeared in the FORTRAN 1 compiler in 1957. They knew about control flow graphs, they knew about finding definition and use relationships, and they knew and actually went about doing that in order to be able to do the optimizations that they did. Now, in the next chart, one was some work that I and John Koch did in establishing the theory of program optimization. We abstracted out of the do loops and so forth the notion of wanting to be able to look at pieces of the program in a very orderly way so that we could do some very fast analysis. One wants to expand the analysis of this as broadly as possible in order to be able to optimize whole programs. So in this, what we invented something called intervals, which allowed us to concentrate and do our analysis one sub-piece at a time. In this particular, in the intervals, the green part would be an inner interval that would be then treated as a node, and then the outer part would be an encompassing interval. We're able in two passes then through the system, no matter how complicated the programs were, essentially two passes over this hierarchy of nodes, some of which contained other nodes, to be able to then analyze and determine what the relationships between the definitions and uses in such a program. So in this particular case, we could determine that all of the definitions in that are shown here do indeed reach node 5, which would be of interest in determining what to do in terms of allocating registers or moving statements around. But there was a little problem with this. We had these tail nodes, like node 8 was part of that inner loop, and we would be optimizing it at the same time we were optimizing the loops. And the loops are the important things to optimize, not these tails. And then along came, in the next chart, some work by Tarjan. And this it was described as Knuth as being an analysis that almost broke. I mean, it's nearly linear. Was able to define intervals which were much more appropriate for this particular problem, and he could do it with almost a linear walk of the program graph. Okay. And it's an elegant, very beautiful piece of work, and much more appropriate for the analysis. That particular piece of work was done in the late 70s. The static single assignment, the next one, is one that was done in the late 80s, and it looks like a complicated sort of thing, but it really is changing the way we're looking at things again. So, and what we're doing here was an observation made by one of my colleagues, Gene Ferranti, who unfortunately couldn't be here, and that if we could reduce a program, change a program to a single assignment program, there are lots of advantages to that one could then do the analysis much more easily. We wouldn't, for every use, there would be one and only one definition that would affect it. Okay, now that is done by introducing what are called phi functions here, and this looks like it's fairly complicated, but if one looks at node 5, one would look back up and find where the use of x is. One would find in node 4, which dominates it, that's the way you get to node 5, this definition of this of x with the little hat, so that's the single assignment of 10, which is really composed of, it's either the definition of x in node 3 or the definition of x in node 9, of x given at 9, and the definition of x given at 11. So then you trace back, and you actually trace back. It's a level of indirections that are going through. So there's a way of kind of noting, putting these things together. What this is going to allow us to do, and which it already has to some extent, we haven't really fully explored this, and we means the compiler community, because there are people using this in various products now, is to be able to collect up information very locally, and when it changes, then to be able to recollect it locally, kind of keep information updated, to be able to do dynamic analysis. So under change, the program itself will be able to keep the information rather than collecting the information. We change it, we throw it away, have to recollect it. So this is going to allow us to be the analysis work to be play a much bigger role in environments. And this has been something that we've always wanted to do, because the analyzer parts of compilers know a great deal about a program, and we need to be able to provide that information to the user, which we can do, but the user then probably wants to change it, do some things with it, or modify the program, and we need to be able to have a much stronger interaction with the program as we involve the user much more in what we're doing. Okay, I'd now like to turn to kind of summarize where we are with the classical optimizers. And indeed, as I've said, they do a wonderful job, but just as I think the languages have not moved very far, we've moved a great deal in terms of algorithms and refining the work. We still have not made it easier for the user, and in the end, that's what we're all about. We wanted to make it easier for the user to do the job. The user still has to, in many of these cases, manage the data. It's assumed that the user is going to place the data somewhere and is going to do the I/O, and this is one of the things we're going to have to change. The compiler must become involved with both optimizing the data and with optimizing the instruction stream. We also, not always, but typically just look at one compilation unit at a time, and that's, we need to expand that and look much further than that. We do the deep analysis to drive the transformations, but we need to widen the analysis and actually think of new ways of doing the analysis. And of course, we do lots of different kinds of transformations. This is only a partial list. There are loads of them. So what are our compiler challenges for 19 that we have now, as I see them? Well, first of all, of course, it's to make compiling fast and programming fast and fun. Now, I think our work should be fun, and I think programming is sometimes a little bit too arduous, and we can do that, I think, in several ways. One is to change the languages. We must change these languages, and the other is to continue to develop our compiler technologies. I was delighted in looking through the list of attendees here today to notice that there are so many students in the audience. And I think that one of the messages I'd like to get across is that even though this is a very old field and is a very rich field in terms of the algorithms and the results that we have, that I think that it's really just at the beginning, and that now, with the capabilities that we have with computers and the kind of interactions that we have, we really need to step back a long way and decide what, and try and change what we're doing. And so I think we need to rethink a lot of these things, and I think to make programming fast and fun has got to be a target. We're struggling too hard in some of these areas. Now, we need to also have portability and performance across systems. We don't want to have to rewrite programs as we move from one to the other, one system to the other. Now, we do well with having standard languages, not so well with having standard interfaces, standard ways of doing things. That's getting better. But in order to get performance, real performance, particularly when the performance depends upon computers that are interconnected, such as parallel performance, and this is an area where I've spent a lot of time, we don't have good methods for doing that yet, the parallel performance in particular. And what in part, it's because we haven't focused on the whole problem yet. So we need to start to think about the whole application and not just parts of it. We also need to think about existing applications. Now, it's very easy to forget about all of those COBOL applications out there that was mentioned this morning. But it's what I believe we need to be able to do is integrate some of those, find interoperability between the COBOL applications, the C and C++ applications, and the FORTRAN applications, whatever. Try and find ways that we can utilize as much of we already have of the existing programs and existing ways of thinking about them. Now, the parallel and distributed systems are just becoming essentially all pervasive. And that's just, certainly we certainly have the laptops and the computers in our desk and so forth that we'll be carrying around. But what will be for our serious computing, much of it will probably be done on a network of computers. Now, where we are right now is that parallel computing is still remaining a little bit isolated from distributed computing. We're starting to see some interesting work going on in networks of workstations, particularly as we're getting very high speed interconnects, so we can use networks of workstations which are being used for just ordinary distributed computing, but gang them up and use them in some of the traditional parallel ways. But what I think we need to do is to start to see the parallel technologies and the distributed technologies come together, so that there isn't a kind of a break in that. Now, there certainly is going to be an important niche for parallel by itself. You know, these massive problems where one has to organize the whole computer collection and the data in order to get the solution, in order to provide the solution. But in general, I think that we'll want to do those on collections of distributed computers. That's going to be coming. In order to be able to do that, we have to manage the data in a different way than we do now. We have to be able to actually step way back from in the application and sort of look at what is the total application look like, what are the computational parts, what are the data parts, what are the data movement parts, and try to, as a unit, look at those. Okay. Now so in terms of meeting these challenges, we need to do whole program analysis and management. I've mentioned that before. We've got to take into the system every part of the problem, if we can, every part of the expression of the problem, acquire knowledge about it, and come up with a whole system solution, which is going to involve compilers and user environments, debuggers, performance monitors, profilers, operating systems, everything. And we have to solve these as a unit. One of my pet peeves is with operating systems, actually, where operating systems have the line between operating systems and compilers sometimes gets very sharply drawn. We have to look at the solution as a whole. The binding issue, the question of when information is known, is we should take advantage of it when we know about it. Link things at compile time if we know it. Link things early. Put things together early on. Or if we don't know it until the very last minute, then find ways of still making it effective. And we have to have feedback mechanisms in order to that information that the user has given us, we can then use in subsequent compiles or subsequent executions of the system. Information that we've collected up from profiling, feed back into the system. We have to be able to work with higher order entities, the arrays, the structures, and pointers if they don't go away, which I wish they would. we don't know what to do with them. So we have to work with those and try to raise that whole level of language so it becomes much more natural, much closer to the problems that are being to the problems themselves. And we need then, of course, to do that in order to be able to get good code out of this. We need to look at the whole storage and process organization and have sophisticated cost models to know how things are related. So in the next chart, this is not really a new compilation model. We have to go to a human-centric compilation model. And a compilation model that involves all parts of the cycles. Okay, before I leave, I'd just like to mention a few things that I think that are about my own the observations in this work that I've been doing in compilers. I've mentioned a couple of the cycles. One is that from problem identification to product has shortened. Another thing I wanted to mention is that the idea of optimization itself has gone through many cycles. And every 10 years I've heard, and sometimes it's less than that, optimization is no longer important. The machines are getting faster and bigger. And then people build a lot of systems on that basis, and then they discover, well, they're in big trouble, and and then optimization becomes important again. We're in a cycle right now where optimization isn't considered very important. This is an interesting point. I'm predicting in 2 years from now we'll be back wanting to have it again. And the reason is because optimization is very much tied to, and if we think of it in a bigger way, is very much tied to function. How much function can you put on your laptop? How much function can you carry around? Well, it's going to be very much in how much can you put in that box. It's very much going to depend on how small and fast it is, how quickly you can get a response. So I think that this is another cycle that I've seen, and unfortunately right now, I think we're not in a very good, we're in the wrong part of the cycle. But don't give up. If you're another one is women in the field. The curious thing is that when I first started, there were more, computer science wasn't a field then, programming wasn't really identified as a career path, and there were more women in my field than, percentage-wise, than there has been at any time since. Okay. Now, I think that's changing again. And certainly with the number of students here, that's going to change rapidly, and it's very essential that it change. And I hope it change. I hope all of you can find a really great career in that. One last piece of I wanted to mention in terms of my own career is that I personally have moved from research to product to research to product, and I have found that is almost essential in my own work. I go down into a product and I rediscover what it takes to build these systems, rediscover all of the details. And then after I've been doing that for 2 or 3 or 4 years, I suddenly kind of surface and say, what's been going on? Come up and look around and find out what is new, what's happening, what the new challenges are, what the new opportunities are. And I think that it's been extremely valuable to me. I would really recommend that kind of thing if it suits your purposes. But it's right now what I'm doing is have resurfaced in some sense from product work, and I'm looking around, and it's very, very exciting what's happening. It's the possibilities for new work in this old field are immense. The problems are exciting. I think we're at the beginning, once again, of a whole new era. I think there's going to be, the next 40 years will probably be much more interesting than the last. More interesting because it's going to be more fun. We can do things quicker. There's going to be new ways of interchanging information, new ways of thinking about things, and what we have to do is to recognize that we've got to think in new ways. And so I challenge all of you, I guess, is to not just do the next epsilon of something. Step back, look for new ways, and always, when you're doing something, think about why you're doing it. I think Anita made a very nice point to think about these things. And before I came down here, I read some of Hopper's papers from the 1950s, and I realized that one of her gifts to us was that she wrote down what she was thinking, why she was doing what she was doing. We need to do that, and not just write it out on email, send it to our friends, send it to our sisters, but to write it down, and however it's going to be archived, so that we can find it, and we need to be able to do that and do it in a very thoughtful way, and that's the way we'll make a difference, It will make a difference to each other. It will make a difference to our field. It will make a difference to the future of where we're going.